Hello, brilliant learners. Let's dive into one of the fundamental wonders of physics: free fall. Imagine you throw a stone upwards. That stone slows down, stops for a moment at the highest point, and then begins to fall back down. But why does this happen? It's because of a mysterious force pulling everything towards the Earth, called the gravitational force. Now, free fall means an object is moving only under this gravitational pull, with no other forces acting on it, like air resistance. Picture a skydiver jumping and just before the parachute opens, falling freely due to gravity. This acceleration that the object gains while falling is called acceleration due to gravity, and we denote it by the letter G, pronounced G. The force exerted on the object by the Earth's gravity is proportional to the object's mass, given by the equation F equals m times g, where F is force, m is mass, and g is acceleration due to gravity. This acceleration g has a value around 9.8 meters per second squared, meaning every second, the velocity of the falling object increases by 9.8 meters per second, if air resistance is negligible. Next, we will explore how this acceleration is calculated based on universal laws. But before that, take a moment and think. When you throw a stone up, does its velocity change on the way up and on the way down? Why do you think so? Pause for 20 seconds to reflect. Welcome back. Let's dig deeper into the invisible force pulling us towards Earth, the gravitational force. Sir Isaac Newton's law of universal gravitation tells us that every two masses pull each other with a force that depends on their masses and the distance between them. Imagine you and your friend pulling on opposite ends of a rope. The bigger your strength, the stronger the pull. The formula is F equals G multiply M divided by D squared, where F is the gravitational force, M is the mass of the Earth. M is the object's mass, D is the distance between the object and Earth's center, and G is the universal gravitational constant. From here, we express the acceleration due to gravity G as G multiply M over D squared for objects close to Earth's surface. Distance D equals Earth's radius R, so G equals G multiply M over R squared. Now, let's pause and think. Why do you think the acceleration due to gravity changes slightly from the poles to the equator? Take 25 seconds to ponder. Great to see your curiosity growing. Now let's calculate the exact value of G right here on Earth's surface. Recall the formula. G equals G times M divided by R squared. We plug in the known constants. G, the universal gravitational constant, 6.7 times 10 to the negative 11th power, M, Earth's mass, 6 times 10 to the 24th power kilograms, and R, Earth's radius, 6.4 times 10 to the 6th power meters. Performing the math, the radius squared is approximately 4.1 times 10 to the 13th meters squared. Then multiplying G and M results in 4.02 times 10 to the 14th Newton meters squared per kilogram squared. Dividing these values, we get about 9.8 meters per second squared. So, that means any freely falling object increases its velocity by 9.8 meters per second, squared every second, ignoring air resistance. Isn't that amazing? Take a moment. Can you predict how the value of G would change if you climbed a mountain high above sea level? Think about this for 20 seconds. Have you ever dropped a paper and a stone from a height and wondered why the paper floats down slower? Well, this is because of air resistance, the force that air exerts against moving objects. The paper's large surface area allows more air to push against it, slowing its fall. But if you could remove the air, imagine dropping them inside a vacuum jar. Both would fall at the same speed. This stunning fact was famously demonstrated by Galileo at the Leaning Tower of Pisa. What does this tell us? That the acceleration due to gravity, G, acts equally on all masses regardless of size or shape when other forces like air resistance are absent. So here's a question for you. Given two balls, one twice as heavy as the other, dropped in a vacuum, which one experiences greater acceleration? Take 15 seconds to answer. Now that we know objects accelerate due to gravity, how do we calculate their speed or distance fallen? Here come the equations of uniformly accelerated motion, where our acceleration a becomes the acceleration due to gravity g. Take v equals u plus at. Here, u is the initial velocity. If an object is dropped, u is 0, but if thrown upwards or downwards, u will vary. Next, s equals ut plus 1/2 at squared helps you find how far the object travels in time t. Lastly, v squared equals u squared plus 2. As relates velocity and displacement without involving time. These equations help us predict and analyze falling objects, from raindrops to astronauts in zero gravity. Here's something to think about. If you drop an object from rest, u equals 0, after how much time will it reach a certain velocity? Pause and consider this for 15 seconds. Let's try a real-life example to see how free fall motion equations work. Imagine a car accidentally falling from a ledge, hitting the ground in half a second. We'll take acceleration due to gravity as 10 meters per second squared to keep things simple. First, to find the speed with which it hits the ground, use v equals a t. Multiply 10 by 0.5 seconds, and we get 5 meters per second. Next, calculate the average speed with the formula, initial velocity plus final velocity divided by 2, which gives 2.5 meters per second. Finally, find the height of the ledge using s equals 1/2 a t squared, that is, 1/2 times 10 times, 0.5 seconds, squared resulting in 1.25 meters. See how physics helps us understand accidents or falls in everyday life. Here's a question. If the time taken for the fall were doubled, how would that affect the speed on impact? Take 20 seconds to think through this. Now let's shift gears and think about when an object is thrown straight up. It rises, slows down because gravity acts downward, comes to a stop at the top, and then falls back down. Suppose it goes up to 10 meters. To find the initial velocity it needed, we use the equation v squared equals u squared plus 2as. At the highest point, final velocity v is 0, acceleration a is minus 9.8 meters per second squared, and displacement s is 10 meters. Solving, we find that u, the initial velocity, equals 14 meters per second. To find the time taken to reach the top, use v equals u plus at, rearranged to t equals u over g, which is about 1.43 seconds. Physics helps us predict everything from sports throws to space launches. Here's a challenge. If you throw the object with twice the velocity, what happens to the maximum height? Think for 20 seconds. So, why should we know so much about free fall and gravity? Well, physics touches every aspect of our lives. Engineers use knowledge about free fall to design safe elevators and analyze vehicle crashes, ensuring passenger safety. Gravity is at the heart of satellite orbits. Without knowing the acceleration due to gravity, space travel would not be possible. Athletes perfect their techniques in jumps and throws by understanding motion against gravity. And who hasn't enjoyed a roller coaster? Designers calculate precise speeds and accelerations to balance thrill with safety, all thanks to free fall physics. Imagine you're an astronaut. Understanding gravity helps you stay on course. Take a moment to reflect. How do you think gravity and free fall concepts apply to your everyday activities? Pause for 25 seconds and think like a scientist. Let's recap all we've learned about free fall. When an object falls only due to Earth's gravitational pull without any other forces like air resistance, it is in free fall. The acceleration it experiences is what we call acceleration due to gravity, or simply g. Near Earth's surface, g is about 9.8 meters per second squared, meaning the object's velocity increases by this amount every second. Using equations of motion, we can calculate how fast the object is moving or how far it has fallen at any moment. Importantly, in a vacuum, where there's no air resistance, all objects fall at the same speed, no matter their weight or shape. This fascinating fact has changed how we understand motion and paved the way for modern physics. Now, can you summarize in your own words why objects fall at the same rate in vacuum? Take 15 seconds to think and reply mentally. Let's test your understanding. Here are some questions related to free fall. 1. What is the value of acceleration due to gravity near Earth's surface? 2. Why does a feather fall slower than a stone when dropped in air? 3. When you throw an object upwards, how does its velocity change with time? 4. If an object is dropped from 20 meters, how long does it take to reach the ground? Consider g equals 9.8 meters per second squared. Pause for 30 seconds and try answering these questions on your own. Let's now go through the answers together. Let's look at the motion graphically. Figure 9.1 on your screen shows an object thrown vertically up. The velocity vector points upwards but shrinks as the object rises until it reaches zero at the peak. Meanwhile, the acceleration vector points downwards throughout the motion, always pulling the object back towards Earth. On the way down, both velocity and acceleration vectors point downwards, hence the object speeds up while falling. This diagram beautifully visualizes that acceleration due to gravity is constant in magnitude and direction, but velocity changes in magnitude and direction. Take a moment and imagine yourself as the falling object moving through these stages. What sensations might you experience? Ponder this for 20 seconds. Here's a handy table, Table 9.1, summarizing the key variables and signs used in free fall and upward motion. Notice the initial velocity is 0 when an object is simply dropped, but positive when thrown upwards. Acceleration due to gravity g is positive when acting downward in free fall, but negative, opposite velocity, when slowing an upward moving object. Displacement describes how far the object moves, whether falling down or rising up. At the highest point of upward motion, the final velocity becomes 0 before the object reverses direction. This table will help you quickly handle problems without confusion about signs or variable meanings. Think about how you'd use this table to solve real-world physics questions. Let's pause for 15 seconds to consider. Let's revisit activity 9.2 for a practical feel of free fall motion. Take a small stone and throw it upwards. Watch carefully. As it ascends, it slows down, reaches the highest point, stops momentarily, and then accelerates downwards. This simple experiment shows how velocity changes direction and magnitude, but the acceleration due to gravity remains constant, always pulling it down to Earth. By observing closely, you understand the invisible force and acceleration acting on every object around us. Try this at home safely, and tell your friends about the physics behind what they see. Which part of the stone's journey do you think lasts longer, going up or falling down? Think for 20 seconds. As we wrap up today's fascinating journey into free fall, remember, Earth's gravitational force silently controls the motion of falling objects around you. The acceleration due to gravity, a cornerstone in physics, explains why and how objects speed towards our planet. Using the powerful equations of uniformly accelerated motion, you can predict speeds, distances, and times for countless scenarios, whether sports, engineering, or spaceflight. Think about the giants of science, like Galileo, who challenged old beliefs through simple free-fall experiments, and Newton, whose laws quantified the universe. Your curiosity and understanding open the doors to exploring even greater mysteries in physics. Keep asking questions and seeking answers. Remember to observe gravity's effects in your daily life. It's everywhere, shaping your world. Until next time, keep exploring and stay scientifically curious.